Hi, my name is Amy Jimenez, and today is April 22nd, and I will be doing a presentation on the retina. So the retina. A brief introduction. So the retina is developed from the same embryonic tissue as the brain. It is the innermost layer of the posterior eyeball, and it's concealed by the sclera. So if we look in the mirror and look at our eyes, we would not be able to see the retina, and that is largely because it's on the posterior aspect of our eyeball, so it's in the back of our eyeball. And it's concealed by the sclera, which we know as the white part of our eyes. This is a light-sensitive layer of tissue that lines the back of the eye, and here at the retina, phototransduction occurs. Phototransduction refers to the process where light energy is converted into electrical signals that the brain can understand. And this is done through photoreceptors that are on the retina. Phototransduction is essential for the brain to perceive a visual picture. The retina contains several neurons which assist in phototransduction and signal processing, and I will go into more detail about what those neurons are in the next few slides. So, just starting with the pathway that light takes towards the retina, light enters the eye and gets refracted twice before reaching the retina. Approximately 2/3 of light refraction is done by the cornea, and the remaining 1/3 of light is refracted by the lens. Once light arrives at the retina, this is when phototransduction actually starts. The impairment of either steps, whether that is damage to the cornea or damage to a lens, if there's any sort of impairment to either of those steps, this would lead to vision damage. And the most common type of vision damage we see through the impairment of either of these steps are myopia and hyperopia. Myopia is nearsightedness, and this is when the focal point falls in front of the retina. And this typically happens when the cornea is too rounded or is protruding too much off of the eyeball. And typically, people with myopia get treated with corrective glasses. And the lens on these glasses are typically indented or concaved to compensate for the rounded cornea. Oppositely, hyperopia is farsightedness, and this is when the focal point falls behind the retina. And to treat this, again, would be prescribing corrective glasses, and in this case, the lens would have a protruding lens to help account for the distance that light travels and help it reach the retina accurately. On this slide is just an image of the eyeball. It shows the anatomy, and you can see the different phases of where light enters and where it leaves the eye, essentially. So you can see the cornea is the outermost layer of the eyeball, the most anterior aspect of the eyeball, and this is where light gets refracted first before it gets to the lens, which is it's drawn here as like a white oval, and this is the lens, which would be the second point of refraction. So phototransduction at the retina. Phototransduction relies on the neurons of the retina. There's 5 types of neurons. There's photoreceptors, bipolar cells, ganglion cells, endocrine cells, and horizontal cells. The retina also contains a dark pigment epithelium layer, which absorbs light that escapes the photoreceptors. This essentially helps prevent distracting light from reflecting inside of the eye and distorting the images. So there's 5 types of neurons in the retina, as I detailed in the previous slide. So there's photoreceptors, and these are neurons that convert light energy into electrical signals. There's 2 types of photoreceptors. There's rods and there's cones. So rods are most helpful for night vision. Objects are often seen in black and white. And in our retina, rods actually outnumber cones by a 20-to-1 ratio. So there's a significantly more amount of rods than there are cones in the retina. However, cones are extremely important because they help with high acuity vision and also allow us to see color. Next are bipolar cells. Bipolar cells receive glutamine transmission from photoreceptors to begin signal processing. Then there's ganglion cells, and they propagate visual stimuli to the brain as their axons make up the optic nerves. And then there's endocrine cells, and they modulate signal between bipolar cells and ganglion neurons. And then lastly, there's horizontal cells. And horizontal cells synapse with photoreceptors and bipolar cells to facilitate lateral inhibition. They help enhance stimulus location and contrast. So essentially, endocrine cells and horizontal cells, they help with communication. They facilitate communication between the cells of that are involved in phototransduction. So in this photo, it depicts just some of the cells that I mentioned in the previous slide. So it shows the direction of light on the left side, and it shows that it enters and hits the ganglion cells first. And it's indicated here that the ganglion cell axons do form the optic nerve fiber. And then after the ganglion cells, light goes towards the bipolar cells, and then it reaches the photoreceptors, which are the rods and cones which we discussed. And then it reaches the pigment epithelium. What's not noted here is the endocrine cells and the horizontal cells. Now they are typically, again, as I said, the medium of communication. So there's not as many endocrine and horizontal cells as there are ganglion and bipolar cells and photoreceptors, but they are distributed across in between these different cells to help facilitate communication. And that is the end of my presentation. Thank you.